Hello, and welcome to the second half of Lecture 20, covering sections 9.5 and 9.6 from Young 14th edition. Here we're talking about the parallel axis theorem and how to calculate the moment of inertia, rotational mass as it's commonly known. In this first example, we're going to get some more practice with the parallel axis theorem. And I've added a couple of clarifying information that should have been in the original body of the problem. One is that the diameter of the rod is 10 centimeters, which was not specified, and I've told you to assume two significant figures on all of the values. Well, what are the values? Well, we have a dumbbell. Our dumbbell has a rod, a connecting rod, that is 20 kilograms in mass. It has spheres at either end that both weigh 40 kilograms, and all of the relative lengths are given as well. We have 30 centimeters from the midpoint to each connection with the spheres, and we have spheres that have a diameter of 0.2 meters or 20 centimeters. Okay, so we are asked a number of questions, all closely related to each other, and that's to calculate the moment of inertia about three different axes, and then to calculate the moment of inertia about an axis that is parallel to the y-axis. Okay, so let's go ahead and jump right into this. Looking at part A, we're going to calculate the moment of inertia about the x-axis. Okay, so obviously the x-axis is our horizontal axis shown here. It is assumed to run through the center of both of the 40 kilogram spheres as well as right down the center of the connecting rod. So in order to do that, we have to think about the moment of inertia of spheres and rods from a table of moments of inertias. Because in this case, our total moment of inertia about the x-axis, so total about the x, is going to be the sum of the moment of inertia of a rod plus the moment of inertia of two spheres. So let's write 2 times the moment of inertia of each sphere. The spheres will be exactly identical to each other in terms of their moment of inertias because the x-axis runs through the middle of both of them. There's no difference there. And here, our rod is actually not behaving like a rod at all. In fact, the fact that I tell you that it has a diameter is a big clue that really what it is a cylinder. It's not a rod in the typical sense of the moment of inertia of a rod. In other words, if you looked up a table of moments of inertias for a rod, you'd see either 1/3 ml squared for a rod rotated about its one end, or 1/12 ml squared for a rod rotated about its midpoint. But for both cases, that's a rod. That's not what we're talking about here. We're talking about a cylinder, just a very long cylinder. And in fact, we don't care about this 60 centimeter length at all. All we care about was the information that I failed to give you. It's 10 centimeter diameter. Okay? So, simply put, what our total moment of inertia will become is the rod effectively becomes a cylinder. So it has the 1/2 and then the mass of the rod times its radius of the rod squared. Okay? Now the spheres are just that. They're spheres. So we'll use the value that we get from a table of common moments of inertia. So 2/5. And then the mass of each sphere, and then the radius of each sphere squared. Okay, so 2/5 mass sphere, radius sphere squared. And then we'll go ahead and plug in our values here. Okay, so we have our 1/2, we'll have our 20 kilograms. Our radius is half of the diameter, so it would be 0.05 meters squared. Then we'll have our 4/5, where I just carried over that 2, or multiply both 2's together. And then we have our 40 kilograms, right? These are big spheres. And then our 10 centimeters, half the diameter, squared. Okay? So when we put that all together, we get a moment of inertia of 0.345 kilogram meters squared. Okay? Of course, we're round to 2 sig figs, so it'd be 0.35 kilogram meter squared. Okay, what's good about this problem, as maybe opposed to some of the ones we did in the previous half of this lecture, is that it really calls into attention the units of the moment of inertia, which, as we're introducing this topic, it's good you have a handle on that. And so I think it bears repeating that the units are kilograms square meters. Really, it's mass area, because that's what the moment of inertia represents, right? It very much represents inertia, the resistance to being moved. The bigger the inertia, the harder it is to accelerate something. And so objects that have a really big moment of inertia want to stay at rest. It's hard to get them moving, right? They're massive, or they're just very awkwardly shaped, or maybe they're both massive and awkwardly shaped. And awkwardly shaped is implying that mass is distributed really far away from the axis of rotation, right? And so that's why the units make sense, because it's mass times area. That distribution of mass makes such a big effect. In fact, we saw in that concept question how it really has a bigger role to play than the actual total amount of mass. Where the mass is located is so crucial. All right, so let's go ahead and do part B, because in part B we'll see what's the new moment of inertia, right, about a different axis. Now let's check our expectations here. Okay, so the first one was x-axis, natural place to start. Part B, we're asked to find the moment of inertia about the y-axis, right there. So would you expect the moment of inertia of this dumbbell, right? Same object, but now rotated in a different way. Would you expect the moment of inertia to be different? Absolutely, because now the mass is distributed differently relative to our new chosen axis of rotation. Well, would you expect the moment of inertia to be, quantitatively larger? Well, yeah. Because you think about it, it wouldn't take much effort to roll the dumbbell along its long axis or along the x-axis. But it's going to take a lot more force times distance, something called torque, something we'll talk about later. It's going to take a lot more torque to rotate the dumbbell this way. It's harder. Just think about physically doing that. Okay? So we should expect the moment of inertia about the y-axis to be significantly larger than the moment of inertia about the x-axis. And in fact, we'll see that it is really quite a bit larger. Okay, so here we'll have I total about the y-axis, and that's going to be the moment of inertia of the both spheres. Okay, so we'll have, let's do the rod first, because the rod we can use a rod about its middle. So I'll do rod mid to imply it's a rod about a midpoint, because that's one of the common moments of inertia that you will see in a table of moments of inertia, a rod about one end and a rod about its midpoint. Okay, that of course assuming the rod has uniform density, unlike in the example we saw in the first half of this lecture. Then we're going to have the two spheres, okay? So let's think about what's going on with the spheres. So each of those spheres doesn't have the y-axis passing through its middle, so we can't just use the ready-made formula for the moment of inertia of a sphere. We can't just use the 2/5, because unlike the x-axis, the y-axis doesn't pass through the middle of either sphere, okay? But they are equal distance from our chosen axis, so we're going to use the parallel axis theorem for both, and then multiply that overall result by 2. That's why I have that leading 2 right there. Okay, so it's going to be 2, and then I'll have the 2/5, and then mass of the sphere, radius of the sphere squared, and then plus the effect of the parallel axis theorem, which is the mass of the sphere, and then times the distance from the sphere to the middle of the sphere. So times h. And I'll call this one hy, okay? Let's see, because I'll need, call it hy, okay? And then, of course, we have to square our hy. All right, and if I add hy into the picture, it'll look like this. It's just going to go from the y-axis to the middle of the sphere. So you can see, by taking a quick look at it, that the value, and then let's just do something, there we go, that the value is going to be 40 centimeters or 0.4 meters. Hy. All right, looks good. Okay, so then let's go ahead and plug in our values. All right, I'm going to go ahead and squeeze them in over here, because otherwise we won't have space for everything. All right, there we are. All right, so our rod then, this is one right from a table. So we'd have 1/12 times the mass of the rod. All right, and then times, and then make a little note there, because I kind of didn't show the same step. All right, because here I had 2 steps, right, where I identified them and then wrote their common formulas. But here, I kind of just I skipped that step, right? So here I'm just going to specify that the moment of inertia of a rod about its midpoint is 1/12 mr for rod, and then radius of the length of the rod squared. And the interesting thing about all those formulas for rods is that it's never like half the length of the rod, which probably would be more analogous to a radius, right? Half the diameter. It's actually the overall length of the rod that's just built into the chosen way that those common formulas are represented. Just take note of that. And of course, it makes absolute sense when you see the way we derived it using calculus in the previous example, in the previous lecture, the previous video, that is. And if you do example 1 for practice, you'll see exactly why it works out to use the overall length, and it's just a choice, just that. Okay, so moving on. So 1/12, that's the coefficient we get from the integral. Check it for yourself. Overall length will be 60 centimeters. All right, so that's just going to be 0.6 meters. And we're going to square that, and then we'll multiply our two spheres offset by the parallel axis theorem. So we'll have our 40 kilograms, and then another set of parentheses, r squared and m squared. All right, so 10 meters squared, and then our hy squared, which is 40, so 0.4 meters, and we'll square that as well. Close up all my parentheses. Okay, so all I've done there is that the fact that no, that doesn't work, because then I'm multiplying the 2 fifths by the wrong thing. Just to fix that up. I was trying to save space, but mathematically it doesn't work, so I'll have to write it twice. That's fine. All right, so let's just do, because here my radius is 10 centimeters, and then I'll just go ahead and do the 2. Write it out. So 40 kilograms, and then the 0.4 meters squared. So you can see that that parallel axis effect has a really big, it's really significant, because we're looking at that. Well, it's got the 40 kilograms, and we're multiplying, so that's the mass of the sphere, the same mass that shows up in the original formula for the moment of inertia. But instead of multiplying by 2 fifths, making it smaller, we're not multiplying by 2 fifths at all. And the distance, instead of just multiplying by the radius, we're multiplying by the distance to, from it to the axis. So having the sphere offset from a rotational axis is a big deal, right? Because the mass now is really far away. So indeed, it's going to make the moment of inertia very significant, especially because it's 40 kilograms, right? And so the effect we're going to get is a dramatically increased moment of inertia of 13.7, which would round to 14 kilogram meters squared. Whoa, right? We're talking like almost 100 times greater, right? In other words, it would take, and this is material that we'll see next week, it would take almost 100 times as much torque, magnitude torque, to get an angular acceleration about the y-axis equal in magnitude as an angular acceleration about the x-axis. It's that much more difficult. Distribution of mass has that much effect. That's the really interesting thing about rotation, right? You can have these dramatic effects with rotation. It's something that we don't necessarily have a good intuition for. When we think about it, we kind of get an idea, if something's twice as heavy, it's twice as hard to lift. But for rotating things, we don't have that. I don't think maybe it's just because of just the experience we've had. We don't have as many rotating objects that we interact with at such a level from such a young age. Okay, so deep thoughts of physics aside, let's go ahead and finish up part C and part D. All right. So in part C, we have the z-axis. Well, the z-axis is a freebie, right? So that's the thing, right? You look at it. Well, the z-axis is exactly the same as the y-axis. So we can say by symmetry, the total moment of inertia about the z-axis has to equal the total moment of inertia about the y-axis. So it must also be 14 kilogram square meters. Because there's no difference. The spheres are symmetric, radially symmetric, and so there's no different distribution of mass, right? So you can just see by looking at it that it's got to be the same as y. Then finally in part D, we're going to talk about a new axis, a y-axis or an alternative y-axis that it runs through the center of the left sphere. Okay, so I will go ahead and label such an axis. All right, we'll do something like this. Have it point straight up. Okay, and I'm going to call this one y prime. All right, let's see. Oh, and that's, I realized I misidentified that. That should be hy, because I was going to use the y, and I was probably thinking ahead. But I'm calling that variable hy, the one that we used in part B. And then here, though, with our y prime axis, we're going to have a new consideration to make for one of the spheres, right? Because now one of the spheres is really far away from the axis, while the other sphere is right on the rotational axis. And so that means we want to label one other thing, which I'll call H prime. All right? We can call H y prime. Why not? Okay, so it'll be this one here. Okay, looks believable. And that one is Hy prime. So it's going to play the same role. We're going to use it with the parallel axis theorem, but we only have to use it for one of the spheres. All right, so here's the question, right? Here's the burning question. Do you think that this one, do you think the moment of inertia about this y prime axis, will it be bigger or smaller than y? You know, because before both the spheres were offset, so they were both adding to an overall effect of the moment of inertia being larger than, you know, certainly larger than around the x-axis. But now one of the spheres isn't, right? So this sphere is definitely going to contribute a much smaller moment of inertia, right? It's going to be much more easy to rotate. Because again, that's what moment of inertia means, right? Big moment of inertia, hard to rotate, right? Requires a lot of force, a lot of torque, right? Small moment of inertia, easy to rotate. But this sphere over here, this one is going to be even harder to rotate now because it's even further away. So does that mean it'll be bigger or smaller? What do you think? Take a minute and think about it, right? Because you should have an idea, not just a random guess. You should actually have an idea. Think about what's happening. Think about the proportionality of moment of inertia relative to radius. Okay? All right, so let's find it. So this will be I total about the y prime axis. Okay, so we're going to have the moment of inertia of the rod about its end. Again, that's one you'd find in the table. Then we'll have the moment of inertia of a sphere about its midpoint, so it's a size sphere. And then we're going to have the one for a sphere plus the offset. So this one is going to be I sphere plus ms times hy prime squared. Okay? So let's plug this all in, see what we get. All right, so this one then will be, I'll write out the expression first, 1/3, because that's a rod about its endpoint. And that's going to be ms and then L squared, mr, excuse me, L squared. And then we're going to have the sphere, so the 2/5 ms rs squared. Then we're going to have the sphere again, so 2/5 ms rs squared. Then we'll have the offset, so this is the ms hy prime squared. All right, let's plug in all our numbers now. All right, so we'll have our 1/3, our 20 kilograms, our 60 centimeters squared. Okay. Then we'll put these two terms together because they are like terms, so I'll just make a 4/5. So we'll have our 4/5 mass of the sphere, so 40 kilograms, and then times the radius of the sphere, the 10 centimeters. Okay, we'll square that. And then we have to add our big offset here. So we'll have, did I leave myself enough space? Not quite, but that's an easy fix. I lost something. What did I lose? I grabbed something I wasn't supposed to. Let's see. There, that'll work. All right, so anyway, so then we've got, the last term, so the 40 kilograms. And then hy prime. Well, how long is hy prime? So we got the 60 and then 10, so 70 and then 80, right? So it's going to be 80 centimeters or 0.8 meters. So it'll be 0.8 meters squared. Well, what was your intuition? Bigger, right? So it's 28 kilogram square meters, right? That's the biggest moment of inertia that we've looked at, right, of the four. And why is that? Well, it's because the radius is squared, and having that sphere further away, twice as far away, well, that's going to more than compensate for having one that is not twice as far away, right? It's the whole nonlinear relationship. Okay, so hopefully this example really kind of puts some concrete context on, working with the moment of inertia, and, just kind of making sense of all this. All right, let's figure out, fix one last little thing over here, messed up. Okay, all right. So, of course, ask me any questions in chat or on messages about a problem like this. So we have one other example that I'm going to show you, and that is example 5. All right. So, In example 5, we're looking at our sphere. All right, so in part A, I say to derive the moment of inertia of a solid sphere with uniform density free to rotate about its center, and then derive the moment of inertia of a solid sphere of non-uniform density free to rotate about an axis through its center, where the density is given with the following formula. All right, so let's go ahead and get into this one. So we'll do our uniform sphere to start out. So let's draw that sphere. All right, so part A. Let's go ahead and draw something that looks like a sphere. Okay, now I'm going to be integrating, so I'm going to kind of show some of the things that I want to discuss. All right, so this is going to represent shells. All right, and then we want to imagine these concentric shells. To make that look sort of 3D, I'll make each of these look like a shell, like so. Okay, and then the same for the outer one. There we go. Right, okay, so there's our shells. Our shell has a thickness of dr, okay, because that's an infinitesimally small thickness. Okay, the overall radius of the sphere is r. Right, so that's going to be big R, like a constant. All right, there we have it. And you can see the big R shows up in part B, right? But our sphere, our constant value, we choose big R. Okay, and so then the overall mass of the sphere is m. So I'll write that over there. Okay, that's the total mass. And this little shell is our spherical shell element. Okay, so spherical shell element, and again that word element just implies that it's infinitesimally small. Element with mass dm. Okay, so the mass of that shell is some mass element dm. Okay, now here's the idea. We're going to really start this, or kind of argue to start it the same way that we would have done the rod, right? Because we want to say, okay, we're going to use the definition of the moment of inertia. Okay, so we'll start with the idea that I equals r squared dm. But here's the thing, okay? If I just did that, if I just took r squared and then I multiplied by dm, well, what would the mass of the shell be? Well, it would just be the surface area of a shell times the thickness times the density. Okay, times rho, right? The volumetric density. But here's the thing. If I did that, I wouldn't get the right answer, because I would just be multiplying r squared by that mass element, and I wouldn't be taking into consideration that mass has a particular shape. Because I could have a mass element that has that same surface area that that also has a 4 pi r squared, right, the surface area of a sphere, but is shaped differently. What if you took the surface area of a sphere and put a big dent in it? Well, it still has the area of 4 pi r squared, but now some of it has a big dent inwards, right? Now some of it comes inwards, right? So the area is unchanged, but its distance from the center has changed. So it isn't enough just to say, oh, okay, let's calculate what the mass is, and then just move on. That will actually give you the wrong answer, okay? And the reason is because the location of that mass matters. So instead, we cheat, okay? So let me show you the cheat, and then I'll just say one other word about why we need to do it, okay? So, but in order to calculate the distribution of mass, okay? We use this idea. We use that I is going to be the integral of moments of inertia itself. So it's going to be, instead of mass elements, it's going to be di shell. So instead what we're saying is we're integrating over the moments of inertia of shells. Because ultimately that's what is happening. We're taking a bunch of these shells of infinitesimal thickness and we're stacking one on top of another, on top of another, another, until we get a small shell. They're called nesting shells, right? We're nesting one on top of another. And then by doing that and considering the shape of the shell, we will get the correct answer for the overall moment of inertia of the sphere. Now, here's the issue though. That means you have to know the moment of inertia of a shell. But that's not really starting from the definition of a moment of inertia, is it, right? That's kind of frustrating. Well, let's write it out, and then we'll say why we have to do that, okay? In this particular class, why we have to do that, okay? So that means that this would become 2/3 and then r squared dm. Why is that? Well, because 2/3 r squared m is the moment of inertia of a spherical shell. Okay, and spherical shells by definition have infinitesimal thickness. They have all of their mass distributed the full radius away from the center of the shell. Okay, so that's an idealized shell, right? Good luck getting a shell that's infinitesimally thin, right? It's got to have some thinness, otherwise it just would fall apart. Plus, how do you get mass in no space? But that's calculus for you. Now, here's the thing. That really begs the question: how would we derive this? How would we derive the moment of inertia of a shell itself? Well, there's ways to do it in this class, right? We could go and we could set up a substitution of differentials, right? We could do something where we were going to, do an integral and think about the overall effect of the shell and how that mass is distributed, and kind of think about how x is related to y for a formula, basically how r squared equals x squared plus y squared, and then we can kind of set it up. But really, the way to do that, the way to find the moment of inertia of a shell, is to use spherical coordinates. So to use multivariable calculus, just set up a triple integral and just find it that way. In fact, that would be even the better way to do it for the sphere. But that is never the way that these textbooks are written. We do not use any cylindrical coordinates, any multivariable calculus at all, okay? Any spherical coordinates, any of that. So that means that we kind of have one hand tied behind our back. It's okay. It's just that if it gives you kind of pause or it makes you a little uneasy that we're not starting with the moment of inertia by this strict definition, that's the reason that we aren't. Okay? All right, but we can definitely proceed from here. So let's do it. So now I want to use the mass element and express the mass element in terms of the radius and the density and so on. So then I'm just going to go on, okay? And just to make it clear, this is for the sphere, all right? I'll write it as such. In fact, S is very ambiguous because shell starts with the same letter. So such to put the word sphere here. Okay. And so then the next step will just look like this. We have our 2/3. See, now that's going to give us the right answer. And then r squared. And then we're going to substitute for the mass element. Okay. So dm is going to become 4 pi r squared times dr times volumetric density. Okay. So that whole thing is dm. So just make it clear, highlighted, highlighted. Right? Those are the same things. That's our substitution. Like we did with the rod, right? Where we replace dm with lambda dx. Here it's just a bit more complicated, right? It's not just like, just a linear thing along a single axis. It's a shape. The shape has a particular formula that gives us the right answer. And instead of lambda, it's rho, because instead of linear density, kilograms per meter, instead it's volumetric density, kilograms per cubic meter. That's what rho is. All right. So now let's go ahead and express rho. All right. So this one we can just get away with just saying, okay, well, and for uniform density, we have that rho is just mass over volume. All right. So it's just total mass over total volume, which is just going to be mass over the volume of a sphere, which is 4/3 pi r cubed. And hey, we're using these formulas and not deriving them, right? So, there's that. And so that means then we can just express rho as, just simply that. We can just do a substitution and just write that for rho. We won't be able to do that for part B because the whole point is in that rho itself is a function of r. Okay, so which means we'll have to do a separate integral as well. But more on that in just a minute. So let's go back to our moment of inertia because we're really ready to wrap up part A. Okay. And here I'll make it obvious that we're going from 0 to big R because we have the correct differential. All right, so let's do that again. 0 to big R, 2/3 R squared, 4 pi R squared. I'm going to put the rho on the really correct side. And then I have a constant, and then 4/3, right, the whole thing is a constant. 4/3 pi R squared dr, the variable r. Let's cancel out anything we can. All right, always a good idea. So we can get rid of a pi. We have a 4 we can get rid of as well. We have a 3 that's going to come up top. In fact, the 3 is going to cancel with the other 3. All right, so this 3 and this 3 cancel. Okay, so yeah, things clean up nicely. So let's go ahead and pull things out. What do we have? Well, then we're going to have, right, I can leave a little bit of space here, not to be crowded in so much. Tad. Okay, so let's go ahead and show that next step though. We have what's going to be left is just a 2m, and then over the constant r cubed, which I mistakenly wrote as squared. Volume isn't squared. Volume is cubic. Oops. All right, let's fix that. Sure, some of you noticed that. All right, so then we'll divide by r cubed. That's the constant, okay? And then what's actually left inside the integral, where we'll do the rules of antiderivatives, is just going to be an r to the 5th, okay? So we look there, we've got, let's see. Oh, right, yeah, so it was r to the 4th, right? But when we do the antiderivative, it will become r to the 5 over 5. So r to the 5th power, that is, over 5, all right? And that's going to be evaluated from 0 to L. Okay, nope, not L. R. I was thinking the rod. All right, looks good. All right, so we'll just go ahead and value those limits. And that's always a nice thing about having one of the limits be 0, right? Makes it a lot easier to evaluate it and not worry about, keeping track of your negatives or anything. That's the same reason I always do the rod about one end, or choose, make it relative to the end. I'll never derive any non-uniform density rod about the midpoint. You could, but then you've got 2 non-zero limits, and it just gives you a lot of extra work. All right, so when we plug in those limits, what do we get? Well, we should get 2/5 mr squared, and it looks pretty reassuring that we do. Let's show it though, right? So I sphere, right, for uniform density at least, so we have a 2 over 5, all right, just like you see in the tables, and then we have a r to the 5th over r squared, and now let me not forget the m. Put the m in the middle. All right, so I have the m right in there. And then, of course, I just wanted to show clearly that it cancels, right? And then we're left with except there's a cubed. I keep doing that. Sometimes, right? Sometimes errors will just carry over. All right, so then that leaves a squared power. So then the final answer is exactly the one you'd find in the table, 2/5 mr squared, where r is the overall radius of the sphere. So there we have it. We showed where it came from. When we look up the moment of inertia of a sphere, we know exactly how to get it, assuming we know the moment of inertia of a shell. Okay, excuse me. So now let's do part B, right? This one's interesting. This one really, it's not just confirming something that we already know, but instead finding something new. Now this one, because our formula here for the density function, okay, and again, units, kilograms per cubic meter, right, because it's volumetric density, it's given with decimals. That means our final answer is going to have decimals in it. I bring that up because I say, in general, when you're calculating moments of inertia for non-uniform density objects, and you're given a density function, and the density function is given as a fraction, you want to keep your final coefficient for your moment of inertia expression as a fraction as well. But here, we have no choice but to work with the decimals because our density function has decimals, okay? All right, so let's do it. All right, so we'll just jump right into kind of the second or third step from part A. So we have I sphere. We know that's going to be 0 to big R. We're going to, and the step I'm referring to is really this one, right? It's really this step right here. This step, okay? So once we've already, argued that the shell idea works and so on. So we have our 2/3. We'll have our r squared. We'll have our 4 pi r squared, just the surface area of each nested shell. And then our rho. This is the part that's new, right? Because we can't just make this argument about rho anymore. We have to actually plug it in. So then we'll plug in our expression for rho. So 14.2 minus 11.6 r over r. And then, yeah, close that parenthesis. And then we'll have our dr. Okay. So, all right, a little bit more complicated. Certainly we'll have a higher order of r because of that functionality. And do notice kind of what this density is telling us. It's telling us that when little r, then the variable little r equals big R, that means that this expression would this be 1, right? This become 1. And so then we just have 14.2 minus 11.6 at the very surface of the shell. So that would be the least dense part of the sphere. And then when the variable r equals 0, then the density goes down, becomes higher and higher. It actually goes up. And so then the densest part of the sphere is the very middle, where it's actually exactly 14.2 kilograms per cubic meter. And the minimum is, if we think about it, it's just the difference between the two. So the minimum would be 0.4 to get to 12, so 2.6, right? So the minimum density is 2.6 on the very outside, and then it's going to go all the way down linearly, in fact, and then have a maximum density of 14.2 at the very center. This would be something like a planet, right? Because planets have dense cores, right? Less dense lithospheres, surfaces, and so on. Okay. So, of course, the densities would be larger then. They'd be all in thousands of kilograms per cubic meter. Okay. So, let's go ahead and work out this process. All right. So, the first thing I'll do is I'll pull some constants out of the integral. So, I'll go ahead and have an 8/3 come out. All right. So, the 8/3 just comes from the 2 times the 4 and then over 3. Okay. We can go ahead and pull out pi as well. Okay. And then let's go ahead and do, think about what the antiderivative will look like. So then I'm going to have, if you think about it, I have an r to the 4th from these two terms, and then I would distribute that into this expression for the density. So I'd have, that would leave me with a 14.2 r to the 5th over 5 once I did the antiderivative. Okay. Likewise, when I distribute the r to the 4th into this one, I have an extra r. So that one would give me 11.6, and then r to the 6th over 6 big R. Okay, and then I'm going to evaluate from 0 to big R. So then you can see that they'll become like terms, right? Because this one seems like it's a higher order term, but of course it has a unit of meters in the denominator. So we'll cancel out. Okay, so then let's go ahead and do that step, evaluate the limits and so on. All right, so what will that look like? So when we plug everything in, I'll just put it right here, we get 8/3. Okay, yep, that's still there. And then, yeah, so it's just going to be, we'll have, this will be a r to the 5th over 5. This one will also be a r to the 5th over 6. And we got a 14.2 and 11.6, so it's just going to become a decimal. And in fact, the decimal it becomes is 0.907, and then the r to the 5th. Okay. So we know we're not done, though, right? Because we've got an expression that is in terms of radius to the 5th power. It doesn't have any mass in it. Excuse me there, a lot of allergies. So what we need to do then is we need to, express our answer in the correct form, right? It's got to have total mass in it, and it's got to be r squared. Well, how do we do that? Well, the way to do it is to do the total mass integral, right? Just like we did for the rod. Okay. So, and we find the total mass integral. Okay. And maybe I should say the word solve, right? Because we're not finding the integral. We're solving the integral in order to find a relationship between m and r. So we solve the total mass integral. So what is that going to look like? Well, that's just going to be m dm, which will then be m from 0 to r. And this will have 4 pi r squared times dr times rho. Okay, because that's it, right? That's the mass of each shell. Okay, here we don't have to notice too that I don't have to do any hand waving here. I don't have to worry about integrating over shells, because for the moment of inertia, the shape mattered. The shape mattered. For the mass, the shape doesn't matter. I just need to find the total mass. Okay, so here it really is just integrating the mass of each shell. Okay, so then what will that look like? Well, that's going to look like this. So 0 to r, we'll have our 4 pi r squared, and then the same expression, 14.2 minus 11.6 r over r dr. Okay, where of course this whole bit here is just rho. Okay, and so then when I actually solve the antiderivative, I'm going to, and actually I'm going to need to fit this on the same row, so I'll bring this over a bit. Okay, so then we'll have 4 pi bracket and then 14.2 r cubed over 3 minus 11.6 r to the 4th over 4r. Okay, and there we have it. All right, looks good. And there I kind of already evaluated the limits of integration. A lot of times, I'll show them in that step. And in fact, let's go ahead and be consistent here. Let's write this as, all right, so this would be r cubed, and this would be r to the 4th, and I'm evaluating from 0 to r, right? Because I've been showing it that way before. Okay, and then if we then go ahead and show this next step, right, once we plug everything in and find the number, and it just ends up being 4 pi, and then times 1.83 r cubed. Okay. So that's a thing, right? What have we found, right? Well, we were given our density function in terms of r, right? So now I've found my total mass in terms of r, and it ends up being proportional to r cubed. Well, of course it does, right? Because it's, it's volume. It is proportional to 3D space. So then how do I make my final expression, right? How do I kind of bring these two things together? Because they're not super well suited to a substitution. I mean, they are in one sense. I could say, okay, I could solve this for r cubed, right? And then just plug it back in, right? So I could just kind of factor out an r squared, or r cubed, that is. Another way to think about it is to think that the moment of inertia will have a certain form, okay? So I could say, and the form of the moment of inertia, excuse me, I need to blow my nose again. All right, so the form of the moment of inertia of, and really any sphere, of any distribution of densities, is going to have the following form. Okay. So we'll say in the form of I sphere is going to be beta, so some coefficient, times mr squared. Okay? So that means that, so then beta is going to equal the moment of inertia divided by mr squared. Okay, well, we know what m is, right? We know that m is just equal to 4 pi times 1.83 times r cubed. Once we multiply that expression for m by r squared, we're going to get something with a fifth. Okay, so then what we have this. We'd have our 8/3 pi times 0.907 r to the 5th, because that's what we got for our moment of inertia. And then we'll take our expression for total mass that we got from our total mass integral, 1.83 r cubed times r squared, cancel out everything except just beta, which will just be a number, just a coefficient. All right, so we cancel out our pi, we cancel out the 5 with the r cubed times r squared, and so then what do we get? Well, we get a decimal, and it ends up being 0.33. 330 if we're working with 3 sig figs. So that means that our final result for our non-uniform density sphere with this particular density function is 0.330 mr squared. And there we have it in the correct form and everything. All right, so good. So I hope this this example got kind of showed you some more practice of how to find moments of inertia for non-uniform objects. Obviously, for objects other than rods, it is a bit more complicated because you have to take into considerations like the nested shell idea that I argued. But the approach besides that is very similar, and I hope you see that, and I hope it all makes sense.